So now we have a SPIRou update by Luc Arnold and Etienne Artigua also. Is that correct? He's online.
He's
so
online. Okay.
Okay.
That's good. Good news. Good afternoon, everyone. Good morning to my colleagues in Canada and Hawaii. So I will give you an update of on the SPIRou instrument. I will talk about some technical aspect, and Etienne will talk about the data reduction software, the latest developments. Okay, so SPIRou has been offered to the community for 3 years now. Jean-François already, this slide is quite redundant with what you heard already. So it's a high resolution spectrograph, spectral polarimeter, at 70,000 resolution, covering 1 micron to 2.35 in the K band. The magnitude range is up to 11 if you want to have a good guiding, and if you are okay to relax the accuracy on the radial velocity, we can observe up to magnitude H14. And the science goal, of course, is looking for exoplanets, high resolution radial velocity, young stars, planet formation, magnitude fields. One of the most important improvements we did on the instrument, it was 2 years ago, we changed the ROMs in the polarimeters, the third generation in green here was not, the transmission was not as good as expected. And the new generation of ROMs now in operation in the CAS unit is the pink, the purple curve. So the transmission of the polarimeter has been improved by a factor of 2 on the blue end of the SPIRou domain, and it was worth doing an update of the ETC. These ROMs have also a smallest wobble, so the injection in the fiber is more stable. The internal stability of the instrument. So if you plot the drift, if you plot the difference between the drift of the science channel with respect to the reference channel, the RMS is always below 2 meters per second, and on the example here it's 0.1 meter per second. And this is when the telescope is not moving, everything is quiet in the dome. And if you see at if you look at the stability during the night, we have some decoupling between the science channel and the reference channel. The science channel is coming from the Cassegrain unit, of course, but the C channel, the reference channel, is coming directly from the calibration unit. And you see, we still have a stability of 0.2 meters per second, even when the telescope is moving and the temperature is changing in the dome, etc. This is a plot showing the stability of the calibration over a full run, the March run. You see that each blue segment is the nighttime, actually, the time during which we are observing. The blue cross at the calibration in the afternoon, and the purple crosses at the morning calibrations. So basically, the instrument drifts by 1 meter per second over one night, And this is what happened when an earthquake is shaking the telescope during the morning calibration. So we will have to remove these calibrations from the database. And we had also some aftershocks 2 nights after. This is a plot showing the radial velocity dispersion versus the extinction, versus the amount of clouds above the telescope. And clouds are expected to change the pupil illumination. And if you change the pupil illumination, you will change the illumination of the grating, and this may change the spectral resolution and ultimately the radial velocity. But what is shown here is that there is no effect detected because the dispersion remains horizontal, remains stable, whatever the extinction variation are. And this is the same kind of plots with the showing the radial velocity dispersion versus the seeing. Again, the dispersion is horizontal. There is no effect on the near field. Apparently, the slit illumination is not affected by the slit stability. Illumination is not affected by the seeing. And this is my last slide. This year, we have completed the full processing of 3 years of data from SPIRou. And all these data are now available for the PIs. It's a homogeneous data set. And the plot here is showing what we get for the Barnard star. This is just what I call raw radial velocity series. There is no systematic error subtraction here. I didn't try to remove a 0-point radial velocity, for example, from reference stars, etc. And what you see that we have a dispersion of 5.2 meter per second air mass. And so this is not 1 meter per second, but it's quite good, especially because nothing more than the CCF radial velocity are plotted here. And Etienne, I don't know if you are here already.
Yeah, I'm here. You hear me? I don't know where my voice is coming from in your room, but okay. So I'll give as Jean-François. Oh, is it okay? All good. Okay. So as Jean-François mentioned, that the DRS is really key in any instrument. You could argue, but I think in SPIRou it's probably even more true than many other instruments, where the pipeline is totally central in the performances, especially for radial velocity. So in 2018, we were naive and we just said, well, we have a plan. We recycle HARPS pipeline. We change a few things at the top of the code, and to match SPIRou format, you press a button, you get a CCF velocity, and voila, you have your time series at the HARPS level. So that was totally naive. And so we started something that was way bigger than anyone would have foreseen. So next slide. Oops, no, yeah. There. So 4 years later, 4 years of much sweating, I think we're pretty much there. There are a few things that and I'll mention a few that we need to finalize, but I think we're mostly there in terms of performances. So 15 FTEs, do the math, it's more than 1% at a time. Obviously, Neil Cook, who spent more than one FTE per year working on that, a lot. Melissa, grad students in our home institution, myself, we worked a lot. And we had to basically invent tools along the way to get the performances we got. I'll mention 3. So it's been researched on astrophysical objects, obviously, but also research into how do you get the darn results at the end. So there's a new telluric correction I'll mention that's used in basically all of your data, all of your SPIRou data. Although the submitted is actually for the second item, so that one is in work. Develop a new PRV measurement method tailored for the infrared. So the line-by-line method is used in Charles Cadieux's and a few other papers also that have been submitted and accepted. And the latest that made a difference a bit regarding what Claire said on these yearly aliases. So we now have 2-dimensional 0-point correction and identify effects that are basically undescribed in the literature. It works, and we're now publishing PRV with sub-meter per second, not points, but constraints. So obviously you fold many observations. You have the time series by Charles Cadieux, TOY 1452. Of course, individual points do not have sub-meter per second, but when you fold, you have a consistent result at the meter per second level on the uncertainties on the planet mass. And in all modesty, we're the only ones doing that in the infrared domain. If you have another instrument, you can read the caption. So basically see that the plots on the right where you have the time series for TOY 1452, there's another instrument observing at infrared wavelengths that basically adds nothing in terms of RV accuracy of case signal, basically the mass, the direct measurement of the mass of TOY 1452 adds nothing. So we're there, and you've seen that graph of the TOY 1452 signal with a little bit of activity, and look at the error bars on that planet mass, basically, or not on the planet mass, but on the K value, 3.5 meter per second, plus or minus less than 1 meter per second. So that sinusoid that you see there is constrained at that level. So next slide. The first new method, and it's not totally new, as many things, it's not always 100% new, is the very standard approach to get from PRV spectroscopy is with the CCF approach. There are lots of other approaches, template matching and so on, but the CCF, you basically reconstruct a very high signal to noise line, mean line, basically weighted mean line, and you measure that velocity on that mean line. And conceptually, it's brilliant. It works very well. It's very useful. We get one for SPIRou, but it is affected by spurious structures, such as residual on the telluric absorption. I'll mention that later, detector defects, and unknown unknowns, any spike in the data that is not consistent with the noise. It's still relevant because it gives you information on the morphology of lines that you cannot get otherwise, but it reaches its limit at some point in the infrared. We developed here for SPIRou a new approach that's kind of line-by-line approach. So you find all lines. So it's a very liberal definition of line. It's basically the domain between two maxima in the spectrum. You get one velocity per line. It's mathematically similar to a template fitting of single lines. Then you do some clever stats, finite mixture model that basically knows, you say, I know there are good lines, I know there are bad lines, and I get a mean of the good lines, so not affected by spurious things that appear in the infrared way more than in the optical, and you get a mean velocity of the good ones. And it's real. The outliers are built in basically in the statistical model, and it's an idea from I got during a coffee break. So enjoy your coffee breaks, from Xavier Dumusc, and he was actually doing that for activity filtering in sun-like stars in HARPS and optical data. So yeah, a constructive coffee break. So this is the graph that we get. I call it the trumpet for obvious reasons. It looks like a trumpet. So it's basically 16,000 measurements of velocity in a Barnard spectrum. And the dark shaded lines are basically good lines, better lines in terms of RV accuracy. So they are better than 200 meters per second per line in RV accuracy, and the lighter shaded are worse line in terms of radial velocity content of the line shape, basically. And you see that in SPIRou data, for anyone that's familiar with infrared astronomy, we get good velocities deep in the water absorption. And if you look at between 100 and 1,800 and 2,000, we have valid measurements between photometric bandpass, between H and K band. So domain that's considered completely rubbish in terms of telluric absorption, we do get valid values. If you look at the lower central plot, there's nothing discrepant there. It's lower quality lines, just in terms of photon noise, but it's not going crazy in terms of gravity. So it shows that we're really able to measure velocities pretty much anywhere in the spectrum, including in the water bands, and there's nothing really discrepant. So that works. That's one of the key elements. The other one, next slide. Oh yeah, so that's a time series. A time series of Barnard with the line by line in green above and the CCF below. So it shows you residuals, type of residuals that you get in the data if you have a mean or even a filtered spectrum and try to get a CCF. It's still pretty good, the CCF at the 5.5 meter per second RMS with the line by line per spectrum. Okay, in this case, we get 2.6 to 2.9 meter per second RMS, depending which bit you look at. Claire mentioned a slightly better value. That's an average per polarimetric sequence. So you get closer to 2 meters per second per sequence. And if you look at that sequence, not quite. If you look at that sequence, the excess RMS, so the RMS that's unaccounted for by the error bars, is about at the 1.1 to 1.6 meter per second. Okay, and we're revisiting optical data, and actually we can derive exciting stuff on published planets. Basically, I won't go into that details, but we're revisiting optical data with that technique, and we're basically finding unpublished things that are pretty exciting. So yeah, nothing more on that, but it's making little babies in the optical also, this technique. So next slide. Tellurics in the infrared.
Etienne, you have 2 minutes left.
Okay, I'll go rapidly. Tellurics in the infrared, it wouldn't be fun if it were easy, it wouldn't be fun. So we worked a lot on tellurics. Basically now we have consistent hybrid model plus empirical data. So you can go to the next slide. Yeah, next slide. So just to show this one, I'll just go, yeah, this one. So basically we fit the model, it leaves spikes, and basically take the best of both worlds with empirical and model. So fit the model, next slide. And then we apply a known, we construct residuals basically and get extremely clean telluric correction. So here you have a before, after. And just to finish, the last 0-point correction is basically we've discovered that stars, there's not only a slight drift of the instrument that are unaccounted for, but there are systematic effects in velocity domain. So you go 2 slides down, I'll show you which one, the killer plot, this one. So basically we discovered that when a star has its line fouling on tellurics at a given velocity, there are residual effects that are probably due to finite resolution effects and so on. So we're correcting a 0-point in velocity domain and not just in time domain, basically. So that's the last thing. Just to finish, wrap it up. 4 years later, SPIRou DRS is now class leading in terms of RV accuracy. Telluric correction is fully implemented, you get the data, it's there. LBL is not formally part of the DRS, but it uses all the outputs of the DRS. We'll give it free on GitHub once the paper is accepted, and the total GP is still being worked on, basically. Questions?
Okay, one question. Yes, go ahead, Pierre.
Microphone. Yeah, so I really like to congratulate you. Remember a few years ago, a number of years ago at SAC, there were a lot of discussions about SPIRou, the science case, but also, the technical challenge. And now it's really nice to see that, it works nice. But there was one magic number, which was heavily discussed, was the 1 meter per second resolution. So it's here, I didn't quite get it, whether you, so I've seen numbers like rather 1.5 to 2. So is it 1 meter per second something which at the end cannot be achieved, or if further development or further data reduction you could get to that magic number?
there may be improvements left. Okay, we're not far from that in terms of excess. So there are two things. I mean, you have a finite signal to noise in your data as any data, and you're not necessarily going to get the photons for 1 meter per second. Okay, so that's one thing. So we are above that in photons, and most cases you want the systematics to be below the meter per second. So for Barnard, for the best stars, we're at 1.6, which may include unpublished planets. So there may very well be a planet at 0.7 meter per second and activity and so on. So we're close to it, but it becomes harder and harder to prove that we're there because there may be some stellar residuals. We know that in terms of external systematic, that's what Luc said, we're well below that in terms of internal drift. So we're close to it, not necessarily, but it's getting harder also from stellar limitation. It's hard to get a star that an M dwarf that you know absolutely that it's stable below the meter per second. So so it's kind of a gray shaded answer, I must admit, but we're at the 1.5-ish with some stellar component that's hard to determine. To say one thing, there's still hints of modal noise and excess noise in terms of the morphology of the noise along the spectrum, and the new slicer may help for that also. And we'll see.
Okay, thank you, Etienne. One more quick question from the Slack channel.
Yes, and Etienne, you have another question in the Slack, but I'm going to ask the first one because it seems shorter, which we'll see. Yeah. Is the RV precision, this is from Sylvie Calbry, is the RV precision affected by the movement of the ROMs during a polarization sequence?
We looked into that and we found no convincing link between position of the ROM and, let's say, a systematic 1, 2, 3, 4. So if you have your PRV and you move your ROMs and you see a systematic pattern, we looked at it a few times and no, we've never seen anything coherent there.
Okay. Thank you very much, Luc and Etienne.